My name is Dr Michelle Dickinson. I've learned that breaking things down is the easiest way to understand them. So join me. We'll break down scientific concepts, meet some amazing scientists and inventors, and help you discover the world around you.
Hi, I'm Dr Michelle Dickinson, and today we're going to be talking about water. Water is an essential part of life on Earth. Without water, life as we know it would not exist. Did you know that 60% of our body is made up of water? And over 70% of the Earth's surface is covered with water. So it really is everywhere. Water is made up of two elements, hydrogen and oxygen. When we say water, we usually think about liquid water, but it can exist in two other states, either a solid or a gas. We often think of water as something that is pure, but actually it's a really good solvent, meaning that sugars, salts, and acids can easily dissolve into it. For example, you'll notice how quickly water mixes with a cordial to make a refreshing drink. Today, we are going to go on a water journey and learn more about the water cycle. By the end of this episode, you will have learned the different stages of the water cycle and how water changes states on this journey. We'll also do an experiment in which you can learn about distillation. You'll make and test your own working model of the water cycle, which could save you if you were ever stuck on a desert island. To do the experiments with me, you will need a large bowl, some salt, warm water, a small bowl or ramekin, plastic food wrap, and a small weight, or I'm using my spoon. Don't forget your notebook and pen so you can write down your observations. If you haven't got those things to hand, go grab them now. A bit later in the show, I'll be checking in with one of my science helpers who'll be joining us from home, and speaking to one of my friends who'll be able to tell us all about their research into water. Okay, let's get started. Water is amazing. It cleans things, hydrates things, and can keep us cool in the summer. Earth is often called the blue planet, and that's because when it's viewed from space, you can see the huge regions covered by the oceans. While water is essential to life, we can't drink the salt water in the ocean, so we need to find our water elsewhere. About 96% of the water on the Earth is in the sea, and only about 1% of the water on Earth is drinkable for us. The remaining 3% can be found in glaciers, snowfields, groundwater, and up in the clouds. Water travels in a cycle, from the ocean to the sky, back down to the earth again as rain, down rivers and under the ground, and out to the ocean again. Water is a chemical made up of two hydrogen atoms and an oxygen atom, and its chemical symbol is H2O. Water comes in three different forms, or states. There's liquid water, which is the one that we all think about immediately. There is ice, which is solid water, and there is a gas stage of water, which is known as steam or water vapor. These stages are all important, as water passes through at least two of them as it goes through the water cycle. We call it a cycle because there is no beginning or end. All of the stages are happening at the same time, somewhere on Earth. For our discussion though, let's start in the sky where water is in its gas state. Air is full of tiny water droplets. We call them water vapor. You might have noticed them when your skin feels sticky on a very humid day. These water droplets are formed when warm temperatures cause liquid water to evaporate. Because warm air rises, it takes the water vapor up with it, away from the Earth's surface and high into the atmosphere. The higher up in the atmosphere you go, the cooler the temperature is. As cooler air can't hold as much water vapor as warm air does, some of the water in the air turns back into a liquid form. This process, when water vapor turns into liquid water, is called condensation. We're going to talk more about condensation later, But you might have seen condensation as a wet, foggy layer on your bathroom windows when the water in the warm air from your shower meets the cold surface of the window pane. Water usually needs a surface to condense onto, so tiny dust particles act as a surface to help clouds to start to form. We call these tiny surfaces cloud condensation nuclei. Cloud condensation nuclei include carbon, soot from volcanoes and industry, sulfates, salt, and dust. Anyway, back to the sky. As the water condenses up there, eventually millions of tiny drops will come together to form larger drops, which will eventually be big enough for us to see as clouds. When we look at them, clouds might look soft and bouncy, but they're actually just very wet as they are made up of tiny drops of water. If we stood in a cloud, it would actually just feel very cold and very wet. If the surrounding air temperature is cold enough, some of these water droplets will solidify so that the clouds will also contain small pieces of ice in them too. When the density of water in the clouds becomes too great and the droplets too large, they start falling to Earth as precipitation. This can be liquid rain, or solid snow, or hail. So far, our water cycle has taken us from liquid water on the Earth evaporating to water vapor in the air, then back down to Earth as rain or snow. Now let's think about the journey that a drop of rain takes once it has fallen out of the sky and landed on the ground. From here, there are a few routes that it can take. It might be absorbed by the roots of a plant and be used for photosynthesis. And you might eat that plant, and the water will then go into you. Then, when you head to the bathroom, that water will travel out of you and into the sewer, through the treatment plant, and then out to sea. Rainwater taken up by the roots of plants and trees can also diffuse out of the leaves and back into the air using a process called transpiration, another important part of the water cycle. Rather than be absorbed by a plant, the raindrop could fall onto a field and just seep into the soil and become groundwater. This is water found underground in the cracks and spaces in soil, sand, and rock, and slowly moves underground, eventually making it to a river or stream and then out to sea. Water that falls from the sky usually ends up in the sea. On its way to the sea, rainwater flows through the earth, dissolving salts from the rocks and soils along the way. Well, water in rivers and lakes isn't salty because only a small amount of salt gets washed into them with the rain. The ocean has had billions of years to build up the salt that is in it, which is why it tastes very salty if you try and drink it. When the heat of the sun warms the surface of the sea, some of the liquid water evaporates and rises up into the air, leaving its salts behind. Now the water is back to where we just started on our journey, as water vapor rising up into the sky on a warm day. This cycle keeps on going, keeping our planet wet, keeping our weather systems forming, keeping our rivers and streams from drying up, and ultimately keeping our planet suitable for life. Now we're going to do an experiment that will help demonstrate the evaporation of water from the sea. Hi Amelia, how are you?
Hi, I'm good, thank you. How about you?
Good, thank you so much for helping me with my experiment today. So we're going to get started and we're going to create basically the water cycle in a bowl. So what I'd like you to do is take some salt, maybe a spoonful of salt, and put it into your large bowl, please. Perfect. Now add some hot water. Be careful because it's hot, maybe about 1 centimetre deep. And then give it a stir so it's all dissolved in until you can't see any more salt particles. Okay, now put a little bit of that water on your spoon, a tiny bit, maybe 2 drops, and blow on it to cool it down. And now dip your finger in and taste it and tell me how it tastes.
Salty.
It's horrible. Okay, it is salty water. That is good. That is not for drinking. That's gross. Okay, next, I want you to take your little bowl and put it in the center of your big bowl, and hopefully you don't have too much water in there, and it should stay dry on the inside. next take your plastic film and you're going to seal your big bowl up. Is it sealed?
Yep.
So is anything happening to the underside of your plastic wrap?
It looks foggy.
That's right, it's starting to look foggy. And so what's happening here is the hot water is starting to turn into water vapor. And then what it's doing is it's touching the plastic wrap and it's condensing. And so if we think about the water cycle, when the hot sunshine is on the ocean, it actually heats up some of the water in the ocean and that rises and condenses. So basically this is a model of how a cloud might form in the atmosphere. So what we're going to do is take our spoon and put it on top of the center of your plastic wrap. And that's just going to create a little divot and a little weight in there. And we're going to leave this for a little bit. And what's hopefully going to happen is that the condensation is going to form, and eventually those tiny water droplets that are starting to form on the surface of our plastic wrap will start to coalesce and come together and get bigger and bigger and bigger and bigger until we get a whole water drop that will hopefully drop into the center of our bowl as rain. So it's time for us to make some rain. We're going to come back in 30 minutes and see what happens, okay? Okay, Amelia, it's been 30 minutes and you should be able to see, can you see that there's some water droplets forming on the underside of your plastic film? You might need to move your spoon to see it.
Yeah, I see a couple.
Okay, and these water droplets are actually the condensation coming together and forming bigger droplets. This is what happens in the clouds to make rain, and we can make it rain on the inside of there. So Amelia, do you think the water on the inside of the bowl is going to be salty?
I'm not too sure.
Okay, well there's only one way to do a test. We're going to open up our bowl and we're going to dip our finger into the water in the middle. And then you're going to taste it.
It's not salty.
It's not salty. That is good. I'm glad it's not salty. So what's happened here is the water has evaporated, and we remember it was salt water before, and it's formed this condensation, and it's basically rained on the inside of the bowl, but the rain is fresh water, and it's left the salt behind in our pretend ocean. And that's what happens actually on the Earth. That's why when you put your tongue out in a rainstorm, it doesn't taste salty. And that is how we get our fresh water in our lakes and in our rivers, even though it's originally come from the ocean.
That's so cool.
It's pretty cool. So you just made a whole water cycle in a bowl and you got to do the taste test. And I'm glad you passed, because I'm really glad yours wasn't salty, because it's a horrible taste. Thank you so much for helping me today, Amelia.
Thank you for having me here.
Okay, after any experiment, we need to write down our observations. These help us to understand our results and make interesting predictions for our next experiments. So, I saw that after a while there was a layer of condensation on the underside of the plastic wrap. And I even saw some droplets of water running down the plastic wrap and dripping into the bowl in the middle. I also observed that I got some fresh tasting water in the small bowl after leaving my mini ocean for about an hour, even though the water it came from was very salty. Now we can look back at our observations and reflect on them by asking questions about why something happened or how we might make it happen again. We're really starting to understand the science behind it. For example, how would that experiment have gone differently if we change a few things about it? What if we mimicked the real water cycle by placing our experiment out in the hot sun? Do you think that would have produced more or less fresh water? Why? What about the shape and size of our bowl? Do you think that changing that could change how much fresh water we collected? Okay, now we know a little bit more about water and the water cycle. We're going to talk to someone who works on one part of the water cycle in their research. Dr Susie Wood is considered one of the world experts in cyanobacteria. She's a senior scientist at the Cawthron Institute in Nelson, where she specializes in freshwater algal blooms. Susie, how are you?
Hi, Michelle. I'm great. I'm really good, thank you.
So we've learnt today about freshwater systems and also about salt waters in the ocean. Can you tell us a little bit about what your job actually is?
Yeah, absolutely. So I'm a freshwater scientist. So I study New Zealand's lakes and rivers, and I'm really interested in understanding what lives in them and why it lives there and how the different sort of things that humans are doing affect the organisms and the quality of our fresh water.
Can you tell us a little about your lab? Like, do you have a lab? Do you just go out to the freshwater with a net? Like, what does it look like?
Yeah, so one of the major projects that we're working on at the moment is we're trying to collect samples from and understand 10% of New Zealand's lakes. So in New Zealand, we have 3,800 lakes. And we've got this huge project with a number of different organisations around New Zealand where we're trying to go and sample 10% of them. So that's 380 lakes right the way across New Zealand. So at the moment, I'm really fortunate that a lot of our time is spent out in the field.
That's amazing. And so do you just go with a bucket and then just pull up a sample, or do you have special ways of collecting things?
So as part of this project, we're trying to understand what the current health of our lakes is like, but also how and why these lakes have changed over the last 1,000 years. And to do this, we take a sediment core from the centre of a lake. And so this is like a drain pipe or a tube of mud that we collect from the sediment. And year by year, sediment is laid down into a lake, and it's like a storybook, if you like, back in time. And we can analyse those different layers of sediment to look at what lived in the lake, what lived around the lake, and how and why water quality has changed.
And so how healthy are our lakes, and are they changing? And if so, what's causing that?
Around about 50% of the lakes that are in lowland areas, so sort of less than 200 to 300 metres, are in poor health. So these are ones which are often in places where the forest has been removed. There might be more urban development, more cities, or more things like farming or forestry around them. So these lakes are in difficulty because we're changing what's happening in the land around the lake, and so that's having an effect on the waterways.
And so what do you love most about your job?
Gosh, there's a couple of things I love about my job, or lots of things I love about my job. One of them, of course, is such a privilege to get out and see all of these amazing places in New Zealand. So these amazing lakes and rivers, and my job has certainly taken me to places around New Zealand and also around the world that I never would have been to.
Now, a lot of students think that scientists and engineers are quite boring and only do science and engineering. Is there anything else that you like to do in your spare time?
I love being in the outdoors, and I've done a lot of sports through my years. So we do a lot of mountain biking and cycling, and any spare moment I've got when I'm not working or doing other jobs around the house, we're out biking in the hills behind our house, and we've got New Zealand's an amazing place to be out and doing that.
And I hear you're actually quite a good cyclist.
Yeah, I did used to cycle for New Zealand, so we used to do a lot of road racing and represented New Zealand in the Commonwealth Games and raced with New Zealand teams, some really amazing women that I got to race with over in Europe and America, and yeah, so it was a neat way to combine doing sport as well as doing my study when I was going through university.
Susie, that was fascinating. Thank you so much for your time today.
No worries, thank you.
The science of the water cycle is fascinating. It's the reason why we have snow and ice. Freezing water is not only useful for the North Pole, but also for one of my favourite snacks, ice cream. The history of ice cream is long and delicious. Historians believe that ice cream was first eaten in China when a mixture of milk and rice was poured into fresh, clean snow to chill and then eat. Ice cream is soft and creamy because the fats in the milk and the cream freeze at a much lower temperature than the water does. So, in most freezers and out in the snow, ice cream stays at just the right creamy texture to scoop up and snack on. Snow actually acts like a net for atmospheric pollution, trapping carbon particles on their way down. This means that air pollution can be brought back down from the air and into the snow on the ground. While heavy snowfall can temporarily improve air quality, as soon as the snow melts again, these pollutants go right back up into the atmosphere or become washed into the groundwater, ending up in our rivers and our lakes. Luckily, there are lots of scientists whose job it is to make sure that the water used in our food is incredibly pure and free of pollutants. And that's the final part of our water cycle, where collected water is treated and processed so that it's safe for us to drink. Water is everywhere, and our freshwater resources are so precious. As it goes through its cycle of evaporation and precipitation, it sustains life both for the plants and animals that drink it, but also acts as a home for those creatures that live in it. Teachers and parents, don't forget to visit nanogirlslab.com, where we have downloadable content to help you continue on your science journey into the wonderful world of water. Thanks for watching. What is the saltiest sea on Earth? If we evaporated all of the water in the ocean, how much salt would be left behind? What would happen if there was no water vapor in the air? What's the difference between water vapor and steam? Does the sea ever freeze? If all the snow and ice on Earth melted, how much more liquid water would there be?